First of all, I'd like to thank the organizer for this nice workshop. Today I'm going to talk about a work I did with my collaborator Ilk, and it's about the maximal freedom in linear perturbation in Nordita at minimum cost. So let me start with an example of what I do not consider minimum cost. Okay, given a particular theory, suppose for instance scalar tensor theory like Nordita or subset of Nordita, study the linear matter power spectrum. What should I do? First, I have to assume a background metric, I for W, like I have to study the background evolution, set the initial conditions, study the attractor solution if I have. Then I have to ask myself, is this solution stable? Then I have to perturb this metric at linear order. At the end, I can calculate. I have to solve the linear equation of motion, I can assume quasi-staticity, or I have to set also the initial condition for the scalar field if we want the exact solution. And at the end, once I solve the linear equations, I can calculate the linear matter power spectrum. So the exercise is this one. If we multiply the number of problems like this by the number of models we can have in modified gravity, the result is a lot of papers on the archive, and this is not what I consider minimum cost. So our aim was to find a description that could unify all these subclasses of Nordita. So can we summarize information better? Of course. We can collect models together, like in K-essence, KGB, or Densky, etc. But if we do so, we will end up with functions instead of parameters, because we are collecting things. And if we want a plot, if we want a prediction, it appears too complicated. It's impossible. We have to give a form to this function. So at the end, we will come back to the original basic models and so. Otherwise, we can identify, like in the effective field theory approach, some operators that in principle are common to many theories, and try to constrain them with observations. My opinion is that in the effective field theory, it's difficult to understand and parameterize this function of time. So we wanted to connect the two approaches. Before doing so, I want to show you the Nordita action, which is the most general action for a single scalar field with the most second derivatives in the equation of motion, and it satisfies the weak equivalence principle. The form of the action is this one. Here we have our matter component, we have our scalar field, its kinetic term, and then we have four functions of the scalar field and its kinetic term. This is the freedom of our theory. So, I want to end this slide with this question. Will we ever be able to constrain the functional form of K, G3, G4, and G5 with observations? Well, just from my own point, when G5x means the derivative with respect to x of G5. Then, to explain, to show what is the maximal freedom, I will start with at the background level. Here we have the usual Friedman equations. We have the matter density, the pressure, the density and pressure of the scalar field, the conservation equation. Here you see this function alpha m. I will come back to this function later. Here we are hiding the first thing. We are hiding the Planck mass, which in this case is a time-dependent function, redefining the densities. So the first thing of this equation I want you to notice that if the mass Planck is varying, the energy density between matter and the scalar field is changed. But now I want to show you the form in terms of the Nordita function of the density and pressure at the background level of in Nordita. So we have many functions, the Rhodesky function, their derivatives. But when we are dealing with background, we are measuring the expansion history of the universe. So from the expansion history of the universe, will we ever be able to constrain kx or g for xx or g5 time? No. At most, we can measure one function of time, like the equation of state or like h of t. So what I mean by maximal freedom is exactly this. At the background level, our freedom is just one function of time. So, and what happens if we go to linear perturbation field? So, we want to generalize the results of the previous slides to linear perturbation field. We have, of course, to assume that the real theory of gravity, which is not obvious, and can be described as a subclass of Rhodesky, because we took our reference as Rhodesky. And if we don't have any other theoretical prior, the resulting freedom is just this I show you in this table. The expansion history, like the Apple parameter and its derivatives, h of t, the value of matter density today, the boundary condition to solve the conservation equation at the background, and 4 arbitrary functions of time, which I'm going to introduce in the next slides. I want also to point out that an equivalent result up to redefinition of the variables was found also using directly the effective field theory approach. But our claim is that our variables, these variables, are more concretely connected with the physical properties of perturbations. So let me introduce you this function. The first function, as I mentioned before, is the effective Planck mass. This is the functional form with respect to the Rhodesky functions. You see that it depends, receives contribution from G4 and G5. It's defined as the normalization of the kinetic terms of the gravitons. But we know that a fixed redefinition of the Planck mass has not a detectable effect. So in general, it can be reabsorbed into the equations, as I did at the background level, also at the linear level. So we will never find the effective Planck mass in our equation. Instead, we will find its first derivative, the Planck mass around rate, which is the first function I'm introducing now. The Planck mass around rate is different from zero in non-minimally coupled theories, as it is clear from this expression. And another important property of the Planck mass around rate is that it introduces anisotropic stress. The second function we find is, we call it kineticity, because it's the most standard kinetic term, as a more complicated form in terms of the Rhodesky function, and actually, it receives contribution from all the functions, k, G3, G4, and G5. It's as I already told, it's the most standard term we have in k-essence, in quintessence, and in a minimally coupled scalar field, of course. But it's not present in archetypal modified gravity models, such as f of r and f of g. In this kind of theories, the kineticity is zero. The third function we have to describe linear perturbations in Rhodesky, we call braiding, alpha b. It receives contribution from just G3, G4, and G5. And it comes from a mixing between the kinetic terms of the scalar field and the metric. Probably the most important properties of this function is that it's responsible for all the new scale dependence beyond the Jeans length. The fourth and last function we have is the tensor speed excess. Contribution, as you see from here, only G4 and G5. Also this one comes, of course, from non-minimal coupled theory, is defined through the definition of the speed of gravitational waves. So it determines the speed of gravitational waves. It can be seen at the with scalar perturbation as an offset between the two metric potentials. It introduces an anisotropic stress independent of the existence of perturbations. So in this table, I finished to introduce these variables. In this table, I want to show how they look like in well-known theories. In lambda CDM, all the alphas are 0, as expected. In quintessence, for example, we have alpha m equal to 0, alpha k different from 0, and the other equal to 0. So basically, there is one alpha different from 0, but everything is determined at the background level. Because once we specify the evolution of the omega matter and the equation of state for dark energy, also the kineticity is completely fixed. In K-essence, things are slightly more complicated. This line, everything is 0 except the kineticity, but here we have a real freedom in choosing the kineticity because the sound speed we can choose freely the sound speed of this here. In another well-known theory like f of r, we see that the kineticity, as announced, is 0, the tensor speed excess is 0, braiding and the Planck mass run rate are different from 0, but they have a constraint. They have to be one the opposite of the other. So in reality, we have just 1 degree of freedom. So summarizing, we started with the Ordensky-Lagrange. We started with 4 functions of scalar field and this kinetic term. If we want to solve for background and linear perturbation theory, we have to choose the functional form of this function plus initial conditions. We ended up with 4 functions of time plus 1 function from the background plus 1 initial condition. So, what are the consequences of this description? The first trigger consequence is that the equation of motions are more compact. The second thing I want you to note is that we can choose freely the time dependence of this function if we want to parameterize them, because they are the maximal real freedom in Ordensky theories. They are independent each other and independent with respect to the background. Also, these functions alpha represent everything that in theory is constrainable by linear observations. Because all the Ordensky models degenerate linearly into these functions. We cannot measure more than this function with linear observation, of course. So I want to spend a couple of words on the quasi-static approximation. I'm not going to criticize the validity of the quasi-static approximation. I just want to show you 2 ways of doing the quasi-static approximation. One is right, probably, and one is wrong. I don't know what is right and what is wrong. But I want to show you the quasi-static thing in the no-breaking case when alpha b is equal to 0. In the Newtonian gauge, we have the 2 metric potential phi and psi, velocity and density of matter, and here we have our so don't worry about B2, B4. They are a combination of the alpha function introduced before, also the CS squared, just for to do it more compact. I wrote these functions. Basically, without doing any approximation, we can decouple this equation up to this level. We don't see the scalar field here in these equations, but this equation is a dynamical equation for for the gravitational potential phi, and this is our anisotropic constraint that relates phi with psi. We could, in principle, solve this equation exactly, but usually we choose something. We choose to be on sub-Jeans length, and we choose also this approximation, which is called quasi-static, in which I neglect time derivatives with respect to space derivatives. I neglect this term with respect to this one. We do these two approximations because we want our famous Poisson equation and an anisotropic constraint like this. Here you see a direct relation between the gravitational potential and the dark matter density perturbations, and here you see a relation between the two gravitational potentials. Here I'm going to calculate the anisotropic stress in two different ways. Okay, here I repeat just what I wrote in the previous slide, and basically the first way is to decouple the exact linear equation as we did, and then we took the quasi-static approximation only on the dynamical equation, which means basically we dropped these derivatives and stop. If we do so, the form of this anisotropic this Lie parameter is this one. We could do another way. First drop time derivatives, and then we could decouple the equation after dropping the time derivatives. The result in this case is this one. And it's different. I don't have any strong claim in this slide, just this result is different. I want just to say it's probably better to use the quasi-static approximation carefully. And just my conclusion, when linear perturbation for the general condensed class of models are described by 5 functions of time and 1 parameter. With this description we think we achieved the separation of different physical effects. We can constrain the values of this function with an observed quasi-Landauskian background, so we separate the effect of linear perturbation from the effects from the background. I want also to mention the I-class project I'm doing with Miguel Zumalacárregui and Julien Lescourbe, in which we implemented this description in the Boltzmann code class. Well, anisotropic stress only if one of the Planck-Master rate of the speed or the speed of tensor is different from 0. A combination of these two functions determines whether the effective Newton's constant is equal to 1 or not. And well, if there is no braiding, the only scale present in our system is the Jeans length. If the braiding is too high, we will have G effective different from 1, but just time dependent in general at all sub-horizon scales. Well, and the positive approximation should be less. Thank you.